Good afternoon and welcome to our Research Exchange series. My name is Kostas Panos. I'm the director of CITRIS and the Banato Institute. And I would like to welcome you here and also welcome our viewers on the web. I've been told to tell you that everything is compostable with today's lunch, except of course for the aluminum foil, but I'm sure you knew that. And a few announcements before I introduce the speaker. The CITRIS Foundry is collecting applications for its spring 2017 cohort. Applications are due on the 26th of March at 11:59 p.m. So keep that in mind. So, of course, the prospective applicants can go online, citrisfoundry.org for more information. Also, I would like to let you know that there is another event happening here in this auditorium at 3 p.m. It is the View from the Talk that is sponsored by the College of Engineering. And today we have Martin Anstis. He's the president and CEO of Lam Research, and he will speak here on innovation-driven leadership, sustaining a high-performing organization. Of course, for those of you who don't know, Lam Research is one of the preeminent equipment manufacturers that supports the semiconductor industry. So it is a true Silicon Valley story. So I hope you will enjoy it here at 3 p.m. Final announcement, there is a CITRIS Foundry Demo Day that is scheduled for the 22nd of March at 6 p.m. in this Banato auditorium. We'll have 6 foundry companies graduating and presenting about what they have accomplished. So it should be interesting. So let me now go to introduce today's speaker. Professor Laura Waller leads the Computational Imaging Lab, which develops new methods for optical imaging with optics and computational algorithms designed jointly. She holds the Ted Van Duzer Endowed Professorship, and she is a senior fellow at the Berkeley Institute of Data Science, or BIDS. She has affiliations in bioengineering and applied science and technology. Laura was a postdoctoral researcher and lecturer of physics at Princeton University from 2010 to 2012, and received the BS, MNs, and PhD degrees from MIT in 2014, 15, and 2010, respectively. She's a Moore Foundation data-driven investigator, a Baker Fellow, Distinguished Graduate Student Mentoring Awardee, NSF Career Awardee, and a Packard Fellow. So please help me to welcome Laura.
Thanks. Thank you. So I understand the audience is really broad, and I wasn't sure exactly what to expect. So please interrupt me if I use some jargon that I shouldn't be using or should be explaining better. But I want to talk about my group's research in computational microscopy and computational imaging in general. So the idea of computational imaging is to design imaging systems. So it's not just image processing, nor is it just building imaging systems. It's sort of the joint design of both. And the idea is that if you think of an imaging system as in this example, a linear system, you've got some object X that you would like to put in. This is what I'm trying to take a picture of. And I'm taking some measurements Y at my sensor. In all of my situations, we're going to have optical systems. So our sensors are like just a regular sensor array of pixels. And I'm going to design some imaging system. And if it's linear, I can represent it by some A matrix that represents the operation that the imaging system does to the object, so I can get the measurement, right? So thinking about it this way, the sort of next step that you want to do is take this measurement Y and figure out what X was, right? So a lot of imaging systems aim to try to make A be something simple so that you can solve this inverse problem really easily, right? And I want to sort of purport that you've got 2 pieces here. So one is the imaging system design, and we are doing this. We're an experimental lab. We're building these systems. We're designing them, and we get to choose what A is within the constraints of physics and cost and simplicity. So this is very much a design problem. There's a lot of art and black magic that goes into it. The second part of it is the algorithm, which is the find X part. And this is much more straightforward, but also not obvious. So we'll see later we sometimes have nonlinear systems or nonlinear measurements, and these X and A and Y can all be like very large pixel count images, and so you run into computational problems. And what's more, the A matrix might not be perfectly invertible, so we have to start to think about what to do in those situations. But the whole idea of computational imaging is that there's synergy in having these things play off of each other. that if you are designing the imaging system and this inverse algorithm in concert together, you can extract synergies that you otherwise wouldn't with just sort of the optics designed alone and the image processing algorithms designed alone. And so I want to give a simple example. I'm going to talk about this example more in detail later. But computational imaging has to involve some sort of hardware design. So here's like our, this is sort of like a really obvious example of computational imaging. There is no lens on this camera. It's just a sensor. So it's a regular camera sensor, but no lens in front of it. And what is in front of it is a piece of glass that has a bunch of bumps on it. They're not carefully designed. This is like literally a piece of privacy glass sticker that you put on your window so your neighbors can't see in. So it creates some bending of the light and messing with the light, but it's totally random, and you just place it at some distance from the sensor. So that's instead of having a lens, we're putting this thing on, right? And so you can imagine a lensless camera with a piece of scattering material in front of it is going to give you a very bad picture. So this is what the picture looks like when I capture it. This is the whole purpose of putting on privacy glass sticker, is to scramble the light. But if you scramble it in a way that you know or can measure, then you can use a computer to then undo the scrambling and get back the image that you had. So we capture this image, looks like garbage, but after solving this inverse problem, we can reconstruct a nice final image. And so there's some nice advantages of this, not that it's just dirt cheap, it's flat, and I'll show you later that we can do some 3D stuff with this. Okay, so this is just a nice sort of example of the pipeline of computational imaging. And I want to talk about two computational imaging systems in this talk. The first one is this one. We call this diffuser cam. This is what it actually looks like. This is just a sensor with a piece of diffuser taped in front of it. And then I'll talk about a microscope that we have in the lab. That's also very simple hardware that with computation can do things that you otherwise couldn't. So diffuser cam, trademarked name, I'm joking, is just what I said. It's just a diffuser, this bumpy piece of glass in front of a sensor, and you're looking out at your scene. Lensless microscopy. So I'm including some of the grad students that did this. If you know them, you can go and ask them for a picture of yourself through the diffuser cam or to play with their toys in the lab. Okay, so let's think about the image formation process. I have some X, that's the picture of me that I would like to reconstruct, and I took some measurement Y, that's the messed up image on the sensor that I captured. And most imaging systems use optical lenses to try to make this A matrix an identity matrix such that what I capture is exactly what I wanted to reconstruct, and therefore there is no inverse problem here, right? The inverse of an identity matrix is itself, and so what you measure is your final result. You don't need an algorithm in there. And that's great. That's a great way to do things. But it creates all kinds of problems because lenses are never perfect. So aberrations, all kinds of like limitations on how you make the lenses. They're big, they're bulky, they take up a lot of space. And so if you can get away from that, why not think about what would be the advantages of doing so? So the diffuser camera has a very different type of A matrix. It's more like this sort of like, we call this multiplexing, is the idea that every measurement is actually a linear combination of measurements from your object at different points. And so if you take a certain point on your object and think about how many pixels it spreads out to in your measurement, then the more pixels it spreads out to, the more multiplexing you have. And is that a good thing or is it a bad thing? It's not clear yet. But we say it's a good thing. And you'll see some obvious reasons why you can't do stuff without it later. But in this case, let's just think like, when is it equivalent to a regular lens? Well, when this A matrix is invertible. So you want to create A matrices that are invertible, but we also need to know them, right? So our object might be a million pixels on our sensor, but this A matrix is going to be a million squared. And I need to know all of the entries of that if I want to be able to invert this thing. And so I hit this calibration problem. So what I would like, if I want it to be invertible, that really means I want every measurement at the sensor for a different pixel in X lighting up should create a unique row in this A matrix. So every row in the A matrix should be unique. And that's true for this diffuser. And it does, and we're spreading the light all over the place, right? A point in our object corresponds to a lot of measurements on our sensor. So basically, our measurement here is going to be the linear sum of sort of the map of what each point in the object maps to on the sensor, sort of summed and weighted over the actual image. Okay, so let me give a more concrete detail about this. So if I take a point source in my object, so I just take my iPhone and I light up the flashlight on it and I hold it far away from this diffuser camera, this is what I measure on the sensor. So this is like we call this point spread function. It's like an impulse function. And it's pretty random because this was just a bumpy piece of glass. This looks like what you see on the bottom of your swimming pool, caustics. If I start moving this point around, however, what happens? So this is cool. So I'm moving the point around laterally, and what's happening is this point spread function is just moving around laterally. And so long as it has a lot of structure, moving around laterally creates a different image for every point on the object, but also I have this really nice model where I only needed to actually measure it once, and then I know exactly what it's going to look like for every other point. And this creates this beautiful convolution model wherein our measurement is just this point spread function thing that we can measure just by lighting up a flashlight in the far field, and it's convolved with the object. So our inverse problem becomes a deconvolution problem, and it should be well posed, and it will be by the way we've chosen this. Okay, so here's the picture that we capture. Here's the picture of me that we reconstruct. Now that you know how it works, you should be able to tell me what this looks like. What is this a picture of? Nobody's good at mind deconvolutions. This is a Thorlab's dog. Okay, so the next step is I want to talk about 3D. So as I take that point source in the far field, so we have our diffuser camera far away, I take that point source and I just change its axial position. And what you're seeing here is that point spread function, this sort of like random caustic pattern, is changing, but in a very specific way again. So now as I go sideways, things just shift sideways. As I go axially, things are magnifying and demagnifying. And so we can put that into our model wherein we still only need this one single measurement, and we know exactly how that thing's going to change over all 3D positions. So now I can write out another linear system where I say my measurement is now the convolution of the object at some depth with the point spread function at that depth, plus the object at all these other depths convolved with this scaled point spread function or this diffuser pattern. Okay, that's great. But now I've got a big problem because I measured 1 million pixels and I'm trying to create, in this case, I'm trying to solve for 4 million different things. And so this is a big problem, right? It's very ill-posed. This is an underdetermined problem. So my measurement is, say, 1 million pixels. That's the number of pixels on my sensor. Now I'm trying to solve for 100 different depth planes, so 100 million things to solve for. And that makes this A matrix fat. And that's bad because I can't invert a fat matrix. So this is where we have to go to tricks. And so one of the standard tricks here is add more information. So add priors about my object. And the way that we're going to solve this problem when it's applicable is to say that it's unlikely that every position in 3D has something going on. There's probably a lot of the 3D space that's just empty. And if that's true, then we can say that this X is sparse. And then we get to use this cool trick that's been really popular recently called compressed sensing. How many people have heard of compressed sensing? Good chunk of the audience. But the idea is more for less, but not really. It's really you're adding a prior in about the object. So if your object is relatively sparse in 3D, which our objects usually are in 3D, then if it has k things that are not 0, then I need only take alpha k measurements, where alpha is a black magic number somewhere between 3 and 10, totally depending on how you took the data. So ours is a pretty good compressed sensing problem. It's not perfect though. So we usually need alpha about 10 or so. But the idea, so here's an example. This is the raw image that I had, and I just threw away 80% of the rows. Just arbitrarily throw away random 80% of the rows and do the reconstruction sort of with this constraint that the object must be sparse. In this case, it's mostly black out here, so that works well, and I can still get a decent reconstruction. So we want to do this for the third dimension, however. And here's an example. So we take a single raw image here, And this object is really a 2D object tilted into the third dimension. And so you can see it, we can reconstruct it at all depths here. So here I'm reconstructing 60 different depth planes. So I'm getting 60 times more voxels reconstructed for than I actually measured, only because I assumed sparsity. So here's a more realistic 3D object. It's a little leaf from a plant. I'm just showing you the 3D visualization of the reconstruction from this single image. Okay, so lest you think that this is just a cute toy that we have in the lab, which it is, and you're welcome to come and play with it sometime. It's very fun to have Facebook pictures that are from Diffuser Cam. We have real science applications for this, and one of the key ones is to take this entire microscope that we've been using in some of our other experiments and shrink it down to just this diffuser in front of a sensor. And you can do this if you don't care about resolution too much, and for this sort of neural activity tracking experiments that we're going to do with it, we don't need really good resolution, and so it's sufficiently good enough to do this. But the beauty of it is that it's small, inexpensive, and I can just take 100 of these things and tile them sideways and get gigantic volumes of measurement all at once. So that's one of our goals. And so what we were doing with it is, by very similar concepts, we're looking at brain activity in 3D. So you've got this beautiful technique of optogenetics wherein a brain neuron fires and it lights up. So it acts like a point source in this 3D volume. And whenever one fires, it lights up. And what you'll like to do is be able to track which ones are lighting up at which points in time. But you've got to do it fast. So you need a single shot method. You don't have time to scan through the third dimension because this stuff is happening fast. So the idea is that most brain neurons are not all lighting up at once, and so you can treat it as a sparse problem and try to solve for which neurons are on in 3D at a time, given some video data. So here's some video data. This is a slightly different method, but pretty similar. And you take this raw data, apply the sparsity constraints. We also account for scattering because the light's passing through scattering material, but that's no problem. You can just pile that into this A matrix that describes your forward model, and then we get back this map of neural activity in a brain. So you can see the two lobes of this zebrafish's brain active at different times. And that's a big goal, is to try to map out neural activity across very large volumes of mouse or hopefully bigger animals eventually. Okay, so the second piece that I want to talk about is a different hardware setup, but it follows the same sort of concept of everything's simple and cheap, and we're going to figure out how to deal with the computational aspects of things on the fly. So this is called the LED array microscope. We copied the original setup from a group at Caltech, and the idea was simply to replace the illumination unit of a typical bright field commercial microscope with this LED array. Adafruit is literally a kid's toy company, and I'll explain how it works. But what's different about this project is it's microscopy. And so in microscopy, everything is small towards the size scale of the wavelength that you're dealing with. And when things get small towards the size scale of the wavelength, you can't just talk about ray optics anymore. So in photography, everything is big, and we can talk about ray optics, and that keeps things, generally, our models can be linear in that case. But now we have to go to wave optics, where phase and diffraction and interference effects matter. And so we need to include these, but we can't measure complex fields. So this is going to create some nonlinearities. So we're going sort of one abstraction outward in the realm of optical abstractions, but still using the simplest possible one. And once you start talking about interference and diffraction, you have to keep track of phase. And phase is something we don't measure directly, but it's extremely important. So here's an example. These are cheek cells scraped off the cheek of one of my students. And if you put them in a microscope without staining or dyeing them, they're completely invisible because they just are basically something of a particular refractive index floating in another refractive index that's similar, water and water. And they don't absorb any light, so you just can't see them. Whereas if you can recover their phase, you get good shape and density information. And this is the quantitative phase, in that this represents how much the phase of a particular light wave is delayed by this object or these cheek cells. So computational imaging, I argue, is necessary here. You have to do computational imaging to get phase, because what we measure is always intensity, which is absolute value squared. So I get to design A, put my object X, which is now complex through some system, but I'm always going to absolute value square it at the end. So my measurement is always this nonlinear measurement of the complex field. So you have to do computational imaging. You have to figure out an A that's going to move phase information about X into Y. And an identity is not going to work here. So there's about 1 billion different ways of doing this. People have been publishing these all over the place on different ways of designing these A matrices. And it's impossible to say which one is the best because it's a nonlinear problem, and so it depends on the object itself. So we're going after really practical and simple ones that are also pretty good for like your generic objects. So here's our microscope, and we're going to do it with illumination coding. So we take away the lamp in the microscope and we put in this LED array. So programmable 32 by 32 array. It's big, like 5 by 5 inches, controlled by an Arduino. We have slightly fancier controllers now to go faster. But the idea is that we can pattern illumination angles. So this thing is just sitting above my sample, and my sample doesn't see sort of any variations in intensity of the light that hits it. It's always just homogeneous intensity, but it's coming from different angles depending on which LED I turn on. So my central LED just illuminates on axis. This LED over here comes in at an angle. So what I'm patterning is illumination angles. And I want to explain why that's useful. Okay, so I'm going to show you that just by doing that, just by patterning angles and taking a bunch of pictures, I can circumvent the diffraction limit of the objective or the numerical aperture of the microscope you're using in order to get higher resolution images. I can get 3D information out of it, or I can change my contrast. And this one's the simplest, so I'll start with it. So bright field is just turn on a bunch of LEDs. It's like a regular microscope. Dark field is when I turn on LEDs that correspond to illumination angles that are so high that they simply cannot be captured by the microscope. So the microscope has a range of angles with which it can capture light, and if you illuminate from higher than that angle, you get black image, except everything lights up that's scattered to higher angles than what you illuminated with. So you get this sort of like picture, you get only the scattered information. We also figured out how to add phase contrast to this. So basically any asymmetric illumination pattern will give you phase contrast. We want to do quantitative phase, so we're going to figure that out later. But you can just time switch between these three and get these 3 different contrast modes, which are the 3 most popular label 3 microscope contrast mechanisms that normally cost a lot of money and require all these specialized inserts and objectives. You just get them by swapping your illumination really quickly with these LEDs. Okay, so probably the coolest thing that we do with this is this gigapixel phase imaging, and this is why we originally built it from the original setup. So the idea is that you want something like this. So I want an image that covers a really large area but also has good resolution. And everybody who's ever used a camera knows that you can't have both. You either zoom in and get good resolution, or you zoom out and get bad resolution across a big area. And so this is an example image where you're getting both, and we're going towards, this is not a full gigapixel image, but we're going towards gigapixel scale images because we can do this. And you can't just do this because when you get that big field of view, it's because you used a lens that has a smaller range of angles, which means it has lower resolution, and there's a diffraction limit you cannot beat. So we're not beating it, we're going around it by taking a bunch of images, so circumventing it. And let me explain how. So here's the big field of view image. So we take a lens that sort of like the zoom out lens. So you zoom out and you get a great big field of view, but if I zoom in on it, I'm just not resolving the smallest features. So big field of view, bad resolution, but I'm gonna mess with my illumination. So I'm doing this like disco patterning of my LED illumination, and these are the pictures that I capture. And they're different. That's good, right? Because every picture I take is different from different illumination angles. So there's some new information in there. And I'm going to say that we can take all that raw data information and reconstruct this higher resolution. And we can do this across the entire field of view of this giant image. Okay, so how does it work? I don't want to get too much into Fourier optics, but basically resolution is all about bandwidth. So if I take the Fourier transform of my object, the larger the bandwidth I have in Fourier space, the better resolution I'm going to have. So I'm starting out with this low resolution lens because I want it to have a big field of view. And then I'm illuminating from high angles. So angle is exactly like spatial frequency. And so these dark field images that I collect actually represent sub-diffraction limited resolution information, but they themselves are not. They're not breaking the diffraction limit. But we can take all of these images that cover different parts of Fourier space. And the idea is that we're just going to stitch them all together in Fourier space to build out a larger bandwidth. This is called synthetic aperture imaging. And from this larger bandwidth, I take the inverse Fourier transform and I automatically have higher resolution. So the hard part is that I didn't measure phase, I only measured intensity. And so when I measured this stuff, I can't just take an inverse Fourier transform without the phase. So I need to add in a phase retrieval piece to this algorithm. And that's exactly sort of the secret sauce to this. And this is really like a duel of imaging methods that have been going on for a long time. There's a lot of people working on this. But you can just throw it into this optimization problem. My measurements represent some forward model of the object passed through my system. And so I just want to minimize some cost function with respect to the object, minimize the difference between the measurements I took and the ones I would have gotten if my current estimate was correct, and then figure out how to update my estimate. So the figure out how to update my estimate is the hard part, and it's generally much harder when you're dealing with this giant nonlinear, non-convex problem that has millions of variables. So we can do it, and I'm not going to talk too much about the algorithms, but one major thing that we need to do is to fix errors in our experiment. So we built the experiment, it's our own fault, but our LED positions are never quite correct, and our images are always full of aberrations. So you can't get better resolution if you've got some aberration destroying it. And these lenses that have low resolution, they also have bad aberrations. So if we don't calibrate this system very carefully, we end up with garbage. We don't get back the resolution we should. And if we calibrate it nicely, we get some nice resolution. So one of the really cool things that we can do is we can parameterize the calibration in terms of something like theta. And then we can fix it, but we don't want to because this like really just destroys the usability of this system. Like this is a simple, cheap system. We want people to build this and use it. And if you have to spend 6 hours calibrating it and then somebody sneezes and it never works again, that's not a system that somebody can use, right? And so we turn to algorithms to solve this problem. And we're calling this algorithmic self-calibration. It's done all over the place in lots of fields. But the idea is that I'm solving some optimization problem to figure out what my object X was, right? I know A, but I don't quite know A, so I'm going to parameterize how I don't know A in terms of theta. So I can just try to do a joint estimation, solve for both X and these parameterized calibration things like theta. And I can put regularizers or constraints on both of these to help make this problem more solvable. But actually, I showed you that we take a lot more data than we need. And so this is a totally solvable joint problem. And we're doing this in every step. We're solving for the aberrations and digitally removing them. Otherwise, this really wouldn't work. Also, the LED positions. So here's a nice example. This is a really nice test resolution target that was made by a company. And if you look, I'm just looking at a few small areas. So here's like some resolution target. So without any kind of algorithm, this is the picture. You don't get good resolution. This is the resolution we reconstruct. And this is the aberration that was there that we removed digitally. So we're solving for the aberrations as well. And as you can see, the aberrations change across the field of view. This is expected. Wide field of view imaging systems always have terrible spatially variant aberrations. And so being able to solve for them in a spatially variant way is really important. So here's sort of like a cool picture that we took. This is cancer cells dividing in a petri dish, and getting at like in vitro live cell samples was hard because you've got to take the data fast before things move. So we did a lot of work to get it. You can see this one's going to spill into a bunch of different cells. So it's one cell dividing itself. So this is really great for biologists who want to be able to look at this kind of like information across thousands of cells at once, but being able to see subcellular things like division. This cell is dying. And there's a lot of like interesting image processing stuff you can do once you have this very large data sets that sort of pile into the data-driven science aspect of things that you can do once you have these really large data sets. Okay, so really large data sets, speaking of, one embarrassing part is that we're actually collecting 10 times more data than we reconstructed. And that was due to the overlap of all of these circles here. And we really wanted to get rid of that. Computational imaging is all about efficient measurement systems, and this is not efficient if I'm taking 10 times more data than I reconstruct. So this overlap is absolutely necessary to get the phase retrieval to work. And we cannot just remove the overlap. We cannot just throw away some of these circles. Things just won't converge. So our solution had to be thinking a little bit differently. And the way we went towards it was this multiplexing idea. So what we do is, first we have a cool way where we just take 4 images and we get the resolution up to twice what it was before. But then beyond that, we take images where we turn on 8 random LEDs, not just one. So instead of scanning through one LED at a time and taking a picture for each, we turn on 8 at a time, a different random 8 every time until we've covered them all. So that's what this disco party pattern was. This is actually the pattern we use. And that means we cover Fourier space 8 times faster. And we don't get rid of the overlap, which we need. So does it work? Of course it works. Low resolution image, single scan LED reconstruction, and then it was taking us 10 minutes. This is a combination of hardware problems and taking a lot of images, almost 300 images. So now when we can just take 1/8 of the images, we get to 40 images, and with some hardware speedups, we get this down to a half a second. And this was absolutely essential for doing in vitro stuff. You can't look at cells on timescales of 10 minutes and expect them not to be moving if they're alive. So we're using only 17% of the data, but it's not compressed sensing. We're just getting rid of redundant data. So this becomes relatively more important as we push this, which we're doing now, towards really large resolution improvement factors. And there's really no limit to that. It's all practical on how much super resolution you can do. Okay, so the last piece that I'll talk about is that we're illuminating this thing from lots of different angles, right? And this just brings up tomography. Anyone who's heard of tomography, sounds like tomography. It's not crazy to think that I could get 3D information out of this. So everything I talked about before, I assumed a thin sample, and sort of cells in a petri dish are very thin. That works well. But when you have 3D samples, everything changes. So here's an example. This is a 3D object in that it's two 2D objects placed at different depths. And what you see as I change which illumination angle I illuminate this from, they appear to shift relative to the other. So as they walk across the screen, the faster they walk, the further they are from focus. If they're right in focus, they won't walk across the screen at all. And the direction they walk in tells you if it's above or below focus. So simple model for this, you've got light coming in at different angles, and you've got these triangles. How far it walks is just a similar triangles argument. So this is what light field refocusing does. It fixes this walking based on this like ray optic similar triangles argument. So this light field refocus you see here is a digitally reconstructed image at 2 different depths. So these are the 2 different depths. We had these 2 resolution targets. One's just rotated relative to the other. And so if I physically focus on them, it looks like this. If I digitally refocus on them with this light field refocusing, it sort of works, but when I zoom in, I'm actually losing resolution. And that's not obvious. So the reason why that's happening is because I'm accounting for the geometric shifts, but I am not accounting for the fact that light spreads out as it propagates. And that's what diffraction is. So diffraction causes, just breaks this light field algorithm because light fields is fully designed for ray optics. And normally you don't care if everything is big, but when things are small, you care. And the only way to fix it is to know phase. So if you want to fix this, you must figure out what the phase was. But that's exactly what we do. We can put it into this big optimization algorithm, but now we're not just solving for the 2D amplitude and phase, we're solving for 2 2D amplitudes and phase at particular distances. And now we can resolve all of these features well. Okay, so I told you that I can take a data set wherein I just change the illumination angle and take a bunch of pictures. And first I said that if the object's thin, I can get high resolution out of it, super resolution, beyond the diffraction limit of the objective. If the object's thick, I can get 3D information. And the obvious question is, can I do both? And so I wouldn't ask if the answer wasn't yes. Okay, so how do I do this? This becomes quite complicated. Here's an experiment where we're doing this. So this is the 2 resolution targets again, one above the other one. And now I've just switched to using a lower NA objective. That means a lower resolution objective. The NA is exactly the inverse of the F number on your digital camera. So here's the 2 different depths, and if I can focus on one and focus on the other with my physical refocusing, so moving the focus knob of the microscope. And because these are low resolution lenses, I'm just not resolving the smallest features. However, if I do my illumination coding and then reconstruct the image, now I can reconstruct features up to the sort of maximum diffraction limit given by these reconstructions. And I'm doing it in both of these two planes. So if you look at the model for this, it actually turns out to be basically exactly the same thing as an artificial neural network. Every node here in the network is the amplitude and phase of the object at that 3D position. And it's a deep network in the sense that you've got a lot of layers here, which account for multiple scattering. So something scatters off one layer to some other part of the 3D object, which can then scatter over here. And so this is a very ill-posed problem. And we just run these optimization algorithms on them as if they're going to work, but we have no proof that this will always work. However, it's very clear empirically that they work in certain situations and not in others. And we're sort of working that out right now, how to know when this works. And our strategy is really to linearize the problem, figure out when it works for the linear problem, and then solve the nonlinear problem, which only makes things a little bit more difficult. But I think it's a really interesting problem possibly for some of the machine learning types in theory to think about, can you prove that this is going to give me the correct answer? Because in medical imaging, I care. Netflix doesn't care if you give the perfect recommendation for the next movie, but I do care that the answer is correct. And we can't prove that our answers are correct right now. So here's just a nice result of a nice 3D object. This is a slightly different method. But you can see the refractive index of these embryo cells as I slide through the depth dimension through the video. And you're seeing different cells coming into focus. We're getting good 3D imaging. OK, so I'm pretty much done. But I want to sort of like make a play for part of why we're doing this. So here's an example where one of my students took all of this stuff with this LED array illuminator and built a 3D LED array illuminator that clicks into this CellScope microscope, which is a 3D printed open source microscope from the Fletcher lab in bioengineering. And they take it out into third world countries where they can use it in the field to do disease diagnosis. So most tropical diseases are still diagnosed by optical microscopy. And getting it into the field where you can do the diagnosis at point of care is huge. So we're adding like huge new capabilities to this cheap, simple, portable microscope with it. We actually run all the code on the phone for some of these algorithms, and that was a real challenge to make them simple and fast enough. They still take forever on the phone. We've also like designed an LED dome that can come in from angles to the full 180 degrees, which buys you even better resolution power. But this thing is super cool because it's designed for manufacture, which means that it's a bunch of design circuit boards which we outsource and have brought back, and then it's just 5 flat circuit boards that we click together, and once they're clicked together, you can just click them into the condenser unit of your microscope. So you can install this thing in about an hour, and we can replicate hundreds of them for a certain amount of money easily, and people can set them up and get them working. And with all of our auto calibration stuff, you don't need to have a fancy like expert aligning them carefully. And so the idea is to get these things so that somebody can build this thing and get it working within a couple of hours so that it becomes adoptable. So making your hardware simple and cheap and easy to use and with these sort of like nice algorithms that are very robust is extremely important for adoption. And that's a piece of that we're really passionate about, trying to get things into a state where they can be adopted easily and are not one-time experiments that are just a paper as the result. So I'm really excited about these kinds of things. Here's a little demo of what they're doing with it. So in computational imaging, I think like the lesson is that we are not currently using available commodity hardware and software at peak efficiency. And this is really a systems integration problem. The hard part of everything we've done is systems integration. We're using off-the-shelf hardware on purpose because it's easy and cheap to replicate. And we're using algorithms that sort of are pretty derivative of some of the big machine learning algorithms and things like that. But I think that it makes a nice point that you can really push the limits of imaging with a little bit of creativity around existing hardware and software toolboxes if you know how each of these work and can sort of design how to put them together in a smart way. And I think there's a lot of opportunity for existing imaging systems to be upgraded a lot by simple and cheap hardware and ideas like this. But they require this sort of systems thinking approach and computational imaging concepts. So that's all that I'll talk about, and thanks a lot, especially to my group who did all this work and to funding sources.
We have time for a few questions.
So it really seems like illumination angle is your sort of method of choice for changing the A matrix. Do you think it is much better to change the angle than, say, defocus or aberration or other more traditional optical transform?
Yeah, so I did my PhD on defocus as the A matrix change for phase retrieval. Illumination angle coding is what gets you to the super resolution. Anything detection side, you can't build up your NA higher because it's too late. You've already lost the frequencies. So that is a huge advantage. I'll also say like the well-posedness of the problem from illumination angle coding is arguably better on the illumination angle side because sort of like you can't write a transfer function for it, but if you linearize it and you could, it would look like a V, whereas defocus is a parabola. And so defocus does great at high frequencies, but it's horrible at low frequencies, where the V shape is a little bit better at the low frequencies, which are the ones that are always problematic. So I argue that it is actually better. And it's faster. It's about no moving parts, I think. That's why it's better.
Not fast for us.
Sure.
Good question here.
So you talked about sort of mostly sensing with some little bit of structured light, kind of stochastic oblique flying spots, kind of structured light. Could you turn the whole thing around and use some of these techniques for special computationally based photomicrolithography?
Yes.
And especially 3D.
Yeah, so we do work in lithography as well, mostly on metrology of masks and wafers to try to recover them afterwards. But there's a huge push in lithography right now, source mask optimization for computational lithography, that is playing around these kinds of ideas. And I think it's a big jump for lithography because they're so used to thinking of diffraction orders and like sort of like poles in your pupil that are now completely changing. So I think it's already happening, so you don't need us.
Yeah. So how are you using this to image the brain? I saw a little bit, but go into a little bit more detail on what you're doing.
Yeah, so the idea is that this diffuser camera, basically you can recover, you just put this thing in front of your sensor and you can figure out where things are in 3D. And so we have these, like in mice, you have some mouse that when a neuron fires, it lights up. And so it's all about just finding the 3D position of what lit up, and then you say that was neuron 10 that lit up. And then over time, when you take a video, you can track which neurons are lighting at which time. And so this is really important because a lot of people are trying to do this, right? Tracking activity in your brain. So for example, what we're going to combine it with a system that can like cause neuron 10 to fire and see which neurons it causes to fire afterwards. So then you can start probing functional brain circuits in real time, which would be amazing. I think the hard part then, though, is that most microscopes have like a 3D volume that only sees 100 neurons at once, and like that's not a brain network, right? Your brain's talking across huge, large scales, and so the more neurons you can get in there, the better. And I don't think we're even close to having enough to fully understand the brain, but that's the goal.
New question here.
This may be related to their questions. I was wondering, I'm accustomed to using light array domes on the macro scale for cultural heritage with polynomial texture mapping, RTI, and do you see applications of these similar methods, or is it just break down when you get to the macro scale?
Yeah, so there's somebody at Rice and Northwestern working on trying to do this on the macro scale with the illuminations, and the idea would be like, if you can illuminate from like this baseline range of angles, it would be equivalent to having a lens of this size, like the acuity that you could get out of it. And so they're trying to do, basically they said like, can we like get the details of a face from a kilometer away? And so theoretically you can. Practically it doesn't work yet, and I'm pretty skeptical that it's going to be super successful because of all of these issues that phase is really sensitive, right? So phase information is happening on the wavelength scale. Like, you get a slight wind blowing through and it changes the refractive index by 10 to the minus 6 over a kilometer. That's a huge phase change. And so I think these are going to create practical problems that will make it very, very difficult.
So what other opportunities do you see to combine the computing part of it with the optics part for maybe people that don't come from an optics background?
Yeah, so I'm actually really excited about like pushing stuff to large scale. So for example, the diffuser camera, we're trying to make it on a Raspberry Pi sensor, which only costs $25 or so. And so if you can make these things for $25, then you could put them everywhere and have them sort of network talking to each other and imaging things across giant baselines. And so I think that would be really exciting. Like you could imagine if you can get it cheap enough, you can start like plastering them all over self-driving cars or something like that to track out 3D information. So I'm really excited about like sort of this lots of sensors together collecting a lot of data to figure these things out, which is also this sort of brain project that we're at. But there's lots of people working in this field doing all kinds of different things. And a lot of it is towards getting at higher dimensions. So spectral information. Your camera might have only red, green, and blue, but you might want a lot of other spectrum. You can start to think about how to multiplex those into your measurements and solve inverse problems with it.
For one of these gigapixel images, how big is the data set and what are the computational requirements?
Yeah, so the data set is like, well, it used to be 10 gigapixels, now it's about 1.2 gigapixels to reconstruct a gigapixel. The cool thing is that I show these really large field of view things, but it's actually like totally independent. So if I take like just a 200 by 200 pixel chunk of the image and all of the those chunks of the image from different angles, I can solve that problem completely independently from the next 200 by 200 pixel chunk with a little bit of edge meshing. And so actually that's what we do. So you just do it, you do it on a patch by patch basis. So it's essentially, it's pretty similar to like what neural networks would require as far as computation. It's an iterative algorithm doing a bunch of Fourier transforms, but you can block it off into chunks such that it's completely parallelizable. So you could actually potentially run this in real time if you had like properly organized parallel computing, which we don't have.
Yes. Hi. Can you actually use your algorithm for sensors that measure capacitance, electrochemical measurements, or impedance, for example, rather than optical input?
Yeah, so like the main conference we go to is computational optical sensing and imaging. So the sensing part is, you could do this for a lot of different things. I know that compressed sensing is becoming popular in all kinds of different sensing fields. So yes, I think this sort of concept or idea is totally applicable. And there's people here at Berkeley working on stuff like that.
Do you have any other questions? One at the front. Okay, one more. One more.
On a big picture, that means we may need to do pre-processing, right? In only some places you need many images to bring back, but some places you may not need. So do we do a pre-processing on those things?
No, we use all of the images for each of the patches. I think you need them all if you don't make any assumptions about, like if you know there's nothing in that part of the image, you don't need to do anything, but that's like up to you to make the assumptions later if you want to save computation. Excuse me.
Thank you very much.
Thanks.